This chapter deals with fluids. We'll be talking about gases and liquids, and a little bit more on the liquids. They're a little bit easier to handle. So swimming's a good activity, good exercise. We have here a person who is experiencing some buoyant force, not sinking, and able to move through the water. The water flows around the person. We have a fluid. So we have solids, gases, and liquids that we can discuss. There's a fourth state of matter, the plasma, that's ionized material. We're not going to cover that. So we have solids with strong bonds between neighbors. It has some shape, some rigidity, has a top surface. If we put energy into this substance, and that can be done by heating it up, then the molecules can move further apart. These bonds can be broken, and we have a situation where the atoms are not right next to each other, the molecules. They can slide past each other, and we have a liquid. Liquids have a top. They take on the shape of the container, but the liquid has a top. If we put more energy into the system, the atoms or molecules become further apart, and we go to gas phase. And the gas has no top. It's a fluid. It flows like a liquid. It takes on the shape of a container, but the gases do not have a top. So you can distinguish it that way. Suppose we have a ton of feathers and we have a ton of bricks. Which weighs more? Well, they're the same weight. We have a ton of each, but their densities are different. Density is defined as the mass of the object divided by the volume of the object. So mass in kilograms divided by volume in cubic meters. Another common unit for density is grams per cubic centimeter. Water is our reference. Water is our standard. And for water, we have 1,000 kilograms per cubic meter. May surprise you just a little bit, but that's the nature of volume and how surprises occur. But water has a density of 1,000 kilograms per cubic meter if the temperature is 4 degrees Celsius. And there's some interesting consequence. As the temperature drops below that, the water becomes less dense, and we get ice forming on top of a pond that you're familiar with as winter is coming. So we have a density calculation. How much mass do we have in kilograms divided by the cubic meters? Which do you think has the greater density, bricks or feathers? Well, the bricks do. Again, density is mass per volume. These objects have the same mass. The only way that can happen here is for this greater volume to have less density. And your book has some common objects that where the density is given. Give you one of those. The Earth's crust is 3.3 thousand times, or 3.3 times 10 to the third, 3.3 thousand, 3,300 kilograms per cubic meter. The overall density of the Earth is above 5,000 kilograms per cubic meter. How is that possible? The crust of the Earth is 3.3 times 10 to the third kilograms per cubic meter. The overall density of the Earth is above 5 times 10 to the third. Well, perhaps you're speculating that there's denser material inside the Earth, in the core, and you'd be correct. Iron and nickel have a greater density than the rocks of our crust, and that pulls up the overall average density of the Earth. So hydroelectric power requires a fluid to move through pipes and drive turbines, push the blades of a turbine and change that potential energy of the water into mechanical energy of the turbine, and further changes to electrical energy. We'll study how generators work in our second semester material. So water, again, water is a reference, 1,000 kilograms per cubic meter. Do you think your density is greater or smaller than water? And you should be saying a little bit greater. It's a situation, if you go into water, you can float if you know how to inflate your lungs well and make your volume a little bit bigger. That'll lower your density. But ordinarily, if you just go into water, you're going to sink because you have a greater density than water. Another difference between the liquids and the gases, the liquids are just about incompressible. Their densities are nearly constant as you apply different pressures, but gases are compressible. If you apply pressure to a gas inside a chamber, the volume of that gas will decrease, the pressure will go up, but you can change the volume. Gases are not incompressible. Solids and liquids are just about incompressible. So you ought to practice with some calculations, such as the mass of the air in our classroom, dealing with lead bricks and so forth. Lead has a density of 11,300 kilograms per cubic meter. Is there any liquid that's more dense than lead? The answer is yes, mercury. And we don't use mercury in our classroom because it is hazardous. But mercury has a density of 13,600 kilograms per cubic meter. But water here flows through, gives up the potential energy to kinetic energy of the turbine, which creates electrical energy. This concept of pressure is defined as the force divided by the area the force is applied on. So pressure is force divided by area. If we have a large area, then the pressure will be small. But deliver that medication in a needle where the area is small, the pressure will be large. Again, pressure is force divided by the area that force is applied. So you have an internal pressure in your body under the skin. So if something comes in here with more pressure, it can overwhelm the interior pressure, and you get an injection. It's always good to get immunized and get some flu shots. Automobile tires, we insert extra molecules to build up the pressure inside the tire. We'll study that in a future chapter. But once the molecules are in there, they collide with the walls, and we end up with a net force that's perpendicular to the wall. That's our gas pressure. So if someone is underneath the water, do you think the pressure is the same on the top of the person and the bottom of the person? Well, you might be familiar with divers. The pressure increases as you go deeper down, and there's a calculation for the pressure. The pressure is equal to the density of the fluid multiplied by our acceleration due to gravity, so 9.8 on the Earth, multiplied by our depth below the surface. So depth below the surface, we have a deeper down in here, the pressure is going to be larger here. And these arrows give us a little indication of force on the person. Pressure equals force over area. You can turn that around. Force is equal to pressure times area. So if we have more pressure, we're going to have more force. We're deeper down, so there's more pressure. This extra pressure here gives a buoyant force to the swimmer, and likely is enough to lift up the swimmer. But all the force arrows are into the body of this person, but the net force, the greater force, is along the bottom of the person here. Will push the person up towards the surface. Now here's an example of this with a liquid, and we have the weight equals mg. We have some height h, and it turns out that the pressure at a certain depth under the fluid can be calculated with the density of the fluid times the acceleration due to gravity times the depth. So h equals 0 is at the surface, and we'll make h positive as we go deeper into the the tank here. On a dam, force is equal to pressure times area. Pressure is equal to the density times the average depth of the dam, and times acceleration due to gravity. Okay, can this work? Can this dam survive? So we'll be, in my class, calculating this. Halfway down the face of the dam, we'll look at an expression for the pressure and see what happens there. There is atmospheric pressure, the gases, but it's more complicated because the gases are compressible. So our density is not uniform as we go up the air column here. Pascal's principle. Pascal's principle. It's the basics of hydraulic systems. So if we apply a small force over here to a piston that has a small area, we'll create extra pressure. And Pascal reasoned that this extra pressure appears everywhere in the fluid. So over here on the bottom in the tunnel, the extra pressure appears everywhere, including at the base of this larger piston. And maybe we have an automobile over here. We've created extra pressure in our reservoir system, and that pressure is transmitted, if you want to say that. It exists anyway in this other part of the fluid. Where the area is large, we're going to get a large force. The force is equal to the pressure divided by area. Now if we multiply both sides by area, that's going to make the pressure larger and the force larger, so we can multiply the force. Sorry, I definitely should not say the pressure gets larger. Pascal's principle says this extra pressure is transmitted undiminished. The pressure is constant on both sides of our system here, but we might have larger area or we might have smaller area, but usually it's larger. In the hydraulic system, we apply a small force to a small area. The pressures are the equal on the two sides. So when we have a large area, pressure is equal to force divided by area. So if the area is large, we're going to need a large force to keep our P2 the proper value. So Pascal's principle, pressure is passed on undiminished, and by making a bigger lid on the reservoir here, we're going to have more force available. This is a machine. We're multiplying force by virtue of having area 2 bigger than area 1. An example of this in a car would be the braking system. The person pushes on the brake pedal with the toe, and perpendicular, parallel now for the force and the to the force. That's good enough. So we apply extra pressure, extra force here. That creates extra pressure. That pressure gets transmitted undiminished, basically through the hydraulic system, and pushes the pad of the brake onto the rotor. Friction slows down the car. So that's our introduction to fluids. We looked a little bit at density, and the fluids have a density in between the density of solids and the density of gases, a little bit closer to the density of the solids. So we'll be discussing the concepts in my class a little bit more, but I'll ask you a few things right now. Why is it that if you hold a pencil between two fingers and then you press in a little bit, that the finger that's in contact with the sharp end of the pencil hurts, but the finger that's in contact with the large end of the pencil does not hurt to push in? Why does that happen? There's the same force on both ends here of the pencil or pen, but the areas are different. On the side where the writing carbon is, that's a small area. So we're going to have a big pressure. Pressure is force divided by area. So with a small area, that medium-sized force becomes a big pressure. So keep practicing with that, and pressure equals our change in our pressure is force divided by area, and we can do various problems where the area is given or the area is unknown. Maybe the force is given or the force is unknown. If we have a situation where we have a force of 1 Newton and an area of 1 meter squared, then we have a pressure unit of 1 Pascal. And just caution you, the Pascal is a small unit, so we'll end up with powers of 10. It'll be not too uncommon. So with that, we're going to stop, and you should read and ask some questions.